On January 22nd, 2026, we are going to witness something that Avi Loeb, the renowned astrophysicist from Harvard, has called a rare alignment. The Sun, Earth, and Comet 3I Atlas will all be positioned on the same plane. Imagine 3 points forming a nearly perfect straight line across the solar system. But here's where it gets even more interesting. Jupiter is on the other side of Comet 3I Atlas, so we'll be watching as the Sun shines its light directly onto 3I Atlas, and we folks here on Earth get to see that comet illuminated in full brightness as it continues its trajectory toward the giant planet. Hit like and subscribe for more sleepy explanation. Now I think we're already seeing some of this effect. Even in the images I captured last night, there's a brightness, a quality to the light reflecting off the comet that seems more intense than it should be given its increasing distance from Earth. But on the 22nd, we're going to see it properly aligned as well. And the difference between the pictures we're taking today versus what we'll capture on the 22nd could be absolutely dramatic. That's why I wanted to document this journey night by night, so we can see this transformation happen in real time. Let me explain why this alignment is so scientifically significant. When the Sun, the object, and the observer are nearly aligned, something fascinating happens with the way light interacts with the dust particles surrounding the comet. The shadows that would normally be cast by these dust particles end up being positioned directly behind the particles themselves from our perspective. This eliminates the dark areas that would normally reduce the object's brightness. It's called opposition surge, or sometimes the opposition effect, and it dramatically increases how bright the object appears to us. Think of it like this. Imagine you're looking at your own shadow on the ground at noon when the Sun is directly overhead. Your shadow is tiny, almost non-existent, right underneath you. But in the evening when the Sun is low on the horizon, your shadow stretches out long and dark in front of you. The same principle applies here with Comet 3I Atlas. When we're looking at it with the Sun almost directly behind us, the shadows disappear and all we see is reflected light, maximum brightness, maximum detail, maximum everything. This is the kind of opportunity that amateur astronomers and professionals alike wait years or even decades to witness, and we're just days away from it happening. So there I was last night, starting my imaging session around 9:30, knowing that each frame I captured was documenting the approach to this historic alignment. The telescope was tracking smoothly. The camera was clicking away, gathering photons from an object that was millions and millions of miles away from Earth. Every few minutes I would check the incoming images on my laptop screen, and with each new frame I became more and more convinced that something unusual was happening with the jets. You see, when I first started observing Comet 3I Atlas weeks ago, this interstellar object was displaying these prominent jets. Long streams of material erupting from the nucleus and extending far out into space. I remember thinking at the time that it looked almost like a cosmic sprinkler system, with material shooting out in multiple directions. Those jets were the result of the comet's icy nucleus being heated by the Sun, causing volatile materials to vaporize and burst outward, carrying dust and debris with them. But what I was seeing last night was different. The jets were still there. In fact, there seemed to be more of them. I counted maybe 4, 5, or 6 distinct jets around the nucleus. But they weren't long anymore. They had become shorter, much shorter. The length had decreased noticeably compared to my observations from previous weeks. And this got me thinking. This got me really analysing what might be happening with Comet 3I Atlas as it continues its journey through our solar system. Was this change in the jets due to the comet's increasing distance from the Sun? As a comet moves farther from the Sun, it receives less solar heating, which typically means less vigorous outgassing and shorter jets. But Comet 3I Atlas was still displaying significant activity, which suggested that something else might be at play. Perhaps the comet's rotation was presenting different active regions to the Sun. Perhaps the composition of the surface materials had changed as outer layers eroded away. Or perhaps we were simply seeing the comet from a different angle that made the jets appear shorter, even though their actual length hadn't changed much. These are the kinds of questions that make comet observation so endlessly fascinating. Every night brings new data, every image reveals new details, and every detail prompts new questions about the nature of these ancient travellers from the outer solar system. I continued imaging throughout the evening, watching as Comet 3I Atlas slowly tracked across the star field. One of the beautiful things about astrophotography is that you can see motion happening in real time if you watch carefully enough. The comet was moving relative to the background stars, and over the course of hours that motion became apparent. Stars that had been on one side of the comet gradually shifted position as the comet continued on its path toward Jupiter. Speaking of Jupiter, let me paint a picture for you of what's coming in the weeks ahead. Right now, Comet 3I Atlas is putting on this spectacular show for us. It's still bright enough to photograph clearly, the details are still visible, the jets are still active, the anti-tail, which I'll explain in detail in just a moment, is prominently displayed. But as the comet continues moving away from Earth and toward Jupiter, it's going to get dimmer and dimmer and smaller in our telescopes. By the time Comet 3I Atlas actually gets close to Jupiter, I expect it will appear as nothing more than a tiny dot even through a decent-sized telescope. The grand display we're witnessing now will have faded to just a pinpoint of light. But here's what makes that future observation so exciting. We'll potentially be able to see that tiny dot in the same field of view as Jupiter and its moons. Imagine that image. The giant planet Jupiter with its bands of clouds and its 4 large Galilean moons, and there, somewhere in that same frame, a tiny speck of light representing Comet 3I Atlas. Now, I don't want to oversell this. I want to set realistic expectations. It's not going to be a dramatic sight. We're not going to see the comet crashing into Jupiter or anything like that. The comet will pass by Jupiter at a safe distance. But the symbolic power of that image, of capturing both the largest planet in our solar system and this visitor from interstellar space in a single photograph, that's something special. That's something worth attempting, even if the comet is barely visible by that point. But I'm jumping ahead again. We've still got potentially 2 or 3 weeks of good imaging opportunities for Comet 3I Atlas before it becomes too dim and too small for detailed photography. And that's why I'm out there every clear night, capturing as much data as I possibly can. Because this window is closing. Every night that passes, the comet gets a little bit farther away, a little bit dimmer, a little bit smaller in our telescopes. Last night was no exception. I was determined to get good data despite some challenging conditions that developed as the night progressed. I started around 9:30, and for the first few hours everything went smoothly. The wind was calm, the stars were sharp points of light in my images, which told me the atmospheric seeing was good. The telescope tracking was accurate. Frame after frame of beautiful data accumulated on my hard drive, and then, around 1:30 in the morning, the wind started to pick up. Now, if you've never tried to do astrophotography in the wind, let me tell you, it's one of the most frustrating experiences you can have in this hobby. A telescope, especially one mounted on a tall tripod or pier, acts like a giant sail. Even moderate wind can cause the whole setup to shake and vibrate. And when you're trying to capture images with exposure times of 30 seconds or a minute or even longer, any vibration at all will ruin your images. The stars turn into streaks. The comet becomes a smear. All that careful setup and all that time waiting for the perfect shot gets wasted. So at 1:30 a.m, when I noticed my telescope starting to shake like a windsail, I made the difficult decision to pack it in for the night. I had already captured between 20 and 30 usable frames by that point, which was enough for some excellent processing work. But part of me wanted to keep going. Part of me wanted to push through and capture even more data. That's the eternal struggle of the astrophotographer. You're always fighting against weather, against equipment limitations, against time itself, trying to gather as much light as possible from these distant objects. But you also have to know when to stop. You have to recognize when conditions have deteriorated to the point where you're no longer getting useful data. So I powered down the equipment, carefully covered everything to protect it from the wind and any potential moisture, and headed inside to start processing the images I had captured. And this is where things got really interesting. When I first loaded the images into my processing software and started working through them, I immediately noticed the anti-tail I mentioned earlier. Now let me explain what an anti-tail is, because it's one of the most visually striking and scientifically interesting features that some comets display. Normally when you think of a comet, you probably picture it with a tail streaming out behind it pointing away from the sun. This is the classic comet appearance, and it happens because the solar wind and radiation pressure from the sun push the comet's gas and dust away from the nucleus in the direction opposite the sun, so the tail always points away from the sun, regardless of which direction the comet is actually travelling. But sometimes, under the right geometric conditions, we can see what's called an anti-tail. This is a feature that appears to point toward the sun rather than away from it. Now, it's not actually pointing toward the sun. What we're seeing is an edge-on view of the dust tail, a perspective effect created by the relative positions of the sun, the comet, and Earth. When the Earth passes through or near the plane of the comet's orbit, we can see this thin sheet of dust particles that the comet has left behind. And from our perspective, it looks like a tail pointing in the wrong direction. Comet 3i Atlas is displaying a beautiful anti-tail right now, and in the images I captured last night, it was more prominent than I had ever seen it before. This narrow spike of a light extending from the nucleus in the direction of the sun was clearly visible in frame after frame. And as I processed the images and enhanced the contrast to bring out faint details, that anti-tail became even more striking. This told me something important about our viewing geometry. It confirmed that we were in that special position relative to the comet's orbital plane where these perspective effects become visible. And it got me even more excited about what we might see on January 22nd, when the alignment becomes even more precise. I spent the next several hours processing those images. This is the part of astrophotography that most people don't see. They see the final beautiful images posted online, but they don't see the hours of work that goes into turning raw camera data into those polished results. I was removing noise from the images using specialized algorithms. I was stacking multiple frames together to improve the signal-to-noise ratio. I was carefully adjusting the color balance and contrast to bring out details while maintaining a natural appearance. And as I worked through this processing, as I zoomed in closer and closer to the comet's nucleus, to examine those jets I had noticed during the imaging session, I started to see details that absolutely fascinated me. The jets were clearly visible, but you had to know where to look. You had to zoom in to the right magnification level and adjust the image display settings just right to make them stand out against the general glow of the coma, the cloud of gas and dust surrounding the nucleus. But once you found them, once your eye knew what to look for, they were unmistakable. I could see 2 jets clearly in some frames. Then as I examined other images from different times during the night, I could make out more of them. 3 jets, 4 jets. In some of the best frames I counted 5 or 6 distinct jets radiating outward from the nuclear region, and they were rotating. This is crucial. These jets weren't static features. As the comet nucleus rotated, which it does continuously as it tumbles through space, the jets rotated with it. Active regions on the surface of the nucleus were being carried around by the comet's spin, and the jets they produced swept around like lighthouse beams. This rotation is one of the reasons why time-lapse sequences of comets are so mesmerizing to watch. You can literally see the comet spinning, see the jets sweeping around, see the whole thing evolving and changing over the course of hours. I made a mental note to create a time-lapse animation from the frames I had captured, aligning them so that the comet stayed in one position while the background stars trailed past. This would show the jet activity clearly and give viewers a real sense of the dynamic nature of this object. But what struck me most as I examined these processed images was how much shorter the jets appeared compared to my earlier observations of Comet 3i Atlas. I pulled up some of the images I had taken weeks ago when the comet was closer to both the Sun and Earth. In those earlier pictures, the jets extended much farther from the nucleus. They were longer, more pronounced, easier to spot without having to zoom in quite so much. Now they were condensed, compressed, concentrated closer to the nucleus. The overall effect was almost like the comet had pulled in its arms, retracting these fountain-like features closer to its body. And I found myself wondering what this meant. Was the comet running out of volatile materials near its surface? Was it simply too far from the Sun now to sustain the kind of vigorous outgassing that creates long dramatic jets? Or was this appearance change simply a matter of perspective and viewing angle? These are questions I couldn't answer definitively sitting alone in front of my computer at 3 a.m. But they're the kinds of questions that make citizen science so valuable. Amateur astronomers around the world are capturing images of Comet 3i Atlas right now. We're all documenting its appearance from different locations with different equipment at different times. And when all of that data gets compiled and analysed, patterns emerge. Changes become clear. The story of the comet's journey through our solar system gets written in light and pixels and data. As I continued processing images, I kept coming back to those jets. I zoomed in as far as the image quality would allow. I adjusted contrast and brightness, trying to tease out every last bit of detail. And in some of the frames, The jets were really quite prominent once you knew where to look. You could see them as distinct features, darker structures against the brighter coma, radiating outward from the central region. I found myself wishing I had a larger telescope, a camera with better resolution, darker skies with less light pollution. These are the perpetual wishes of every amateur astronomer. We're always limited by our equipment, our locations, our atmospheric conditions. Professional observatories with their massive mirrors and perfect mountaintop sites can capture details we can only dream of. But there's something special about doing this yourself, about being the one standing out in the cold darkness, operating the equipment, making the decisions about exposure times and tracking rates and focus points. You develop a connection with the object you're observing that you just don't get from looking at someone else's images. Comet 3I Atlas had become my obsession over the past weeks. Every clear night I was out there photographing it. Every day I was processing the previous night's data and planning the next observing session. I'd watched it brighten and then begin to dim. I'd seen its jets evolve and change. I had followed its path across the constellations as it moved through our solar system on its way toward that distant encounter with Jupiter. And now, with this upcoming January 22nd alignment, I felt like all of these observations were building towards something significant. A culminating event where all the geometric factors would align perfectly and we would see Comet 3I Atlas in its full glory, illuminated by the sun in a way that only happens under these rare circumstances. Avi Loeb's article about this alignment had really captured my imagination. Here was a serious academic scientist, someone at the top of the field of astrophysics, writing about the same event I was preparing to photograph from my backyard. He had explained the physics of the opposition effect, how the elimination of shadows dramatically increases an object's brightness when viewed nearly in line with the sun. And he had noted that this kind of alignment has only occurred one other time with a comet in recorded observational history. One other time. That's how rare this is. Think about all the comets that have passed through the inner solar system over the centuries. Think about all the observations that have been made since Galileo first pointed a telescope at the heavens. And in all that time, in all those observations, this particular geometric configuration has only been documented once before, and now it's about to happen again, and we have the technology to capture it in unprecedented detail. This is why I do this. This is why I spend hours in the cold darkness setting up equipment and troubleshooting technical problems and battling wind and clouds and light pollution. Because every so often something truly special happens, something rare and beautiful and scientifically significant, and if you're prepared, if you've put in the work to develop your skills and acquire the right equipment and learn the techniques, you can be there to document it. You can contribute actual scientific data to our understanding of these mysterious visitors from the outer reaches of space. As I finally wrapped up my processing session in the early hours of the morning, I looked at the collection of images I had created. They showed Comet 3I Atlas in various stages of processing. Some were wide-field views showing the comet and its anti-tail against a rich star field. Others were zoomed in close, revealing the structure of the jets and the bright glow of the inner coma. I had created the time-lapse sequence I had envisioned, showing the comet remaining stationary while the stars streaked past, and you could see the subtle changes in the jet structures as the nucleus rotated beneath its veil of gas and dust. But I also knew these were just the beginning. These images from last night were good, but they were capturing Comet 3I Atlas before the alignment. They were documenting the approach phase. The really spectacular stuff was still to come. January 22nd was still days away, and if the weather cooperated, if the seeing conditions were good, if my equipment performed flawlessly, I might be able to capture something truly extraordinary. The thought of that possibility kept me energized despite the late hour and the physical fatigue from hours of standing in the cold and then sitting hunched over a computer. This is the anticipation that drives scientific discovery. The knowledge that you're on the verge of witnessing something important. The hope that your observations might reveal something unexpected. And Comet 3I Atlas had already proven itself to be full of surprises. From the moment it was first detected and classified as an interstellar object, it had been defying expectations. Its trajectory, its brightness, its activity level, its jet structures, everything about it had been somewhat unusual and unexpected. And now it was giving us this rare alignment opportunity. this chance to see it under near-perfect illumination conditions. I thought about all the other people around the world who are probably doing exactly what I was doing right now, processing images from the previous night, planning the next observing session, sharing data and comparing notes through online forums and social media. The global amateur astronomy community had rallied around Comet 3I Atlas, recognizing it as a special object worthy of intensive observation, and that community would be crucial in the coming days, because while I could observe from my location when my weather was clear, there would be times when clouds rolled in, or equipment failed, or other obligations prevented me from imaging. But someone else, somewhere else on the planet, would have clear skies. They would be capturing data, and collectively, we would build a comprehensive record of this comet's appearance during this historic period. That's the beauty of distributed observation networks. No single observer can watch an object continuously. The Earth rotates, clouds form, equipment breaks, life intervenes. But with observers spread across multiple continents and time zones, someone is always watching, someone is always gathering data. The sun never sets on the global amateur astronomy community. I made myself a cup of coffee as dawn started to brighten the eastern sky outside my window. The observing session was over, the processing work was done, but my mind was still racing with thoughts about Comet 3I Atlas and what the coming nights might reveal. I pulled up the weather forecast for the next several days, hoping to see clear skies predicted. The forecast showed mixed conditions, some clear periods interspersed with clouds, but nothing that looked like it would completely shut down observations. Good enough. I would take what I could get. I started thinking about the technical aspects of imaging the comet on January 22nd specifically. Would I use the same equipment setup I had been using, or should I modify something to optimize for the brighter illumination conditions? Should I adjust my exposure times to account for the increased brightness? Should I try to capture more frames to build a larger dataset for stacking? Should I attempt any spectroscopic observations to analyze the composition of the jets and coma? These were all decisions I would need to make as the 22nd approached. But for now, I had images to share. I had data to contribute to the collective knowledge about this remarkable object, and I had a story to tell about what I had observed and what was coming. I began uploading the processed images to my computer, preparing to share them with the community and with all of you who have been following this journey with me. And as I looked at those images, at the delicate structure of the anti-tail, at the subtle jets radiating from the nucleus, at the overall glow of this visitor from beyond our solar system, I felt that familiar sense of awe that first drew me to astronomy years ago. We live in an age where anyone with determination and relatively modest equipment can contribute to scientific discovery, where amateur astronomers can capture images that rival professional observations from decades past, where we can watch in real time as comets evolve and change and reveal their secrets, where we can participate in documenting rare astronomical events that happen only once or twice in recorded history. And Comet 3I Atlas is giving us all of that and more. It's giving us a show, a performance, a display of the raw power and beauty of nature operating on a cosmic scale. Gas and dust erupting from an ancient ball of ice and rock, sunlight reflecting off countless tiny particles, jets rotating as the nucleus spins through the void, all of it happening millions of miles away, yet visible to us here on Earth through the miracle of telescopic observation and modern imaging technology. As I sipped my coffee and watched the sky continue to brighten, I thought about the generations of astronomers who had come before me. The ones who had to sketch what they saw by eye through crude telescopes, the ones who waited decades for the invention of photography to allow permanent records of celestial objects, the ones who painstakingly measured positions on glass plates and calculated orbits by hand. They would have given anything to have the tools we take for granted today. And yet, despite all our modern technology, despite our sophisticated cameras and computer-processed images and real-time data sharing, we're still driven by the same fundamental curiosity that motivated those early astronomers. We still want to know what's out there. We still want to understand how these cosmic visitors behave. We still feel that thrill of discovery when we notice something new or unexpected in our observations. Comet 3I Atlas represents all of that. It's a mystery we're actively working to solve, with every observation, with every image captured, with every data point collected, We learn a little bit more about this particular object and about comets in general. We add to the collective human knowledge about our solar system and our place in it. And in just a few days, on January 22nd, we're going to add an especially important piece of data to that knowledge base. We're going to document what happens when a comet is viewed under these rare opposition illumination conditions. We're going to see firsthand how the elimination of particle shadows affects the perceived brightness and appearance of the object. We're going to capture images that can be compared with theoretical models and used to refine our understanding of comet composition and structure. This is real science. This is discovery in action, and it's happening right now with this comet during this alignment, and you're part of it just by being here and following along with these observations. I finished my coffee and pulled up my imaging calendar for the next week. Clear skies were forecast for this evening, so I would be back out there with the telescope, capturing another night's worth of data on Comet 3I Atlas. Each night between now and the 22nd was precious. Each observation session was an opportunity to document the comet's changing appearance as we approached that perfect alignment. And then, after the 22nd, I would continue observing as long as the comet remained bright enough and large enough to capture meaningful detail. I would watch it fade and shrink as it continued its journey toward Jupiter. I would try to capture that future image I had envisioned, with the comet as a tiny dot somewhere in the same frame as the giant planet and its moons. I would document this entire arc of the comet's passage through our planetary neighbourhood, because that's what observers do. We watch, we record, we share, we build the story frame by frame, night by night, observation by observation, and the story of Comet 3I Atlas is far from over. In fact, with the January 22nd alignment approaching, we're just getting to the most exciting chapter. The anti-tail that appeared in my images from last night represents something I need to explain in much greater detail, because understanding this feature will completely transform how you interpret the images I'm sharing with you. When I first noticed how prominent this anti-tail had become, significantly more visible than in any of my previous observations of Comet 3I Atlas, I knew we were witnessing something special about our viewing geometry and the comet's orbital mechanics. Let me take you deeper into what creates this phenomenon and why it matters so much for our upcoming observations on January 22nd. The anti-tail isn't actually a separate tail structure at all. It's an optical illusion created by our perspective, but calling it an illusion doesn't diminish its importance. In fact, this perspective effect tells us crucial information about where we are relative to the comet's orbital plane, and how dust particles are distributed in the space around the nucleus. When Comet 3I Atlas releases dust particles from its nucleus through those jets we've been discussing, those particles don't just disappear into space, they follow their own orbits around the Sun, orbits that are slightly different from the comet's orbit, because the particles have different masses and velocities. Over time, these dust particles spread out along the comet's orbital path, creating a thin sheet or disk of material that marks where the comet has been. Now, most of the time when we observe a comet, we're looking at it from an angle where we see this dust disk edge on or nearly edge on, and it appears as the classic tail stretching away from the Sun. But occasionally the Earth passes through or very close to the plane of the comet's orbit. When that happens, we get a special view looking almost directly down into that disk of dust particles, and because of perspective, that sheet of particles can appear to extend in the direction toward the Sun rather than away from it. Think of it like looking at a dinner plate from the edge versus looking at it from above. From the edge you see a thin line, from above you see the full circular shape. With Comet 3I Atlas right now, we're transitioning through different viewing angles of that dust disk as Earth moves through space and the comet continues on its trajectory. The prominence of the anti-tail in last night's images tells me we're getting closer to that optimal viewing angle, where we can see the full extent of the dust distribution. This is directly related to why the January 22nd alignment is so significant. On that date, not only will we have the Sun, Earth, and Comet 3I Atlas positioned on the same plane for optimal brightness through the opposition effect, but we'll also have a near-perfect view of the comet's dust distribution. We'll be able to see both the anti-tail and the regular solar wind-driven tail simultaneously, giving us a complete picture of how dust and gas are moving away from the nucleus in all directions. The images I captured last night showed this anti-tail extending quite far from the nucleus. When I measured it in my processing software, I found it stretched for a considerable distance, creating this spike or jet pointing back in the direction from which the comet had come. And it was remarkably straight and narrow, which told me the dust particles creating this effect were confined to a relatively thin plane, rather than being scattered widely above and below the orbital plane. This kind of detail matters to professional astronomers studying comet dynamics. The width and brightness distribution of an anti-tail can reveal information about the size distribution of dust particles, the timing and intensity of past outbursting events, and the forces acting on those particles as they slowly drift away from the nucleus. Amateur observations like mine, when combined with data from other observers and from professional facilities, contribute to building detailed models of how comets shed material and how that material evolves over time. But beyond the scientific significance, there's also just the sheer visual beauty of seeing this feature so clearly displayed. In many of my processed images from last night, you could trace the anti-tail across the frame, a delicate spike of light pointing in what seems like the wrong direction, until you understand the geometry that creates it. It's a reminder that astronomy is as much about perspective and viewing angles as it is about the objects themselves. What we see depends critically on where we are when we look. As I continued working through the image processing in those early morning hours after I'd packed up the telescope, I started creating different versions of the same images optimized to show different features. Some versions were stretched to emphasize the faint outer regions of the coma and tail structures. Others were processed to maintain detail in the brighter inner regions near the nucleus. Still others were optimized specifically to show those jets I had noticed during the imaging session. This multi-scale processing approach is essential for comet imaging because comets have such an enormous dynamic range. The nucleus region can be thousands or even millions of times brighter than the faint outer reaches of the tail. No single image processing approach can show all of these features simultaneously at their best, so you create multiple versions, each one revealing different aspects of the comet's structure and appearance. When I zoomed in on the nuclear region to examine the jets in detail, I had to be very careful about how I adjusted the image processing parameters. Push the contrast too far and you start seeing artifacts and noise patterns rather than real structure. Don't push it far enough, and the subtle jets remain invisible against the general glow of the inner coma. Finding that sweet spot where real features emerge without creating false details is part art and part science, developed through experience and practice. In the best frames from last night's session, I could clearly identify multiple jets once I had the processing dialed in correctly. There was one particularly prominent jet that appeared in nearly every frame, extending from the nuclear region toward the upper right in my images. This jet seemed to be one of the most active sources of material, consistently visible and relatively bright compared to the others. Then there were several fainter jets visible at different position angles around the nucleus. What fascinated me was watching how these jets appeared to shift position from frame to frame as I worked through the image sequence chronologically. This was the rotation of the nucleus becoming visible in the data. The comet was spinning, probably completing one full rotation every several hours based on what I was seeing, and as it spun, the active regions creating these jets were carried around. A jet that appeared at the top of the nucleus in one frame would gradually shift to the side in later frames, and eventually new jets would become visible as previously hidden active regions rotated into view. I created an animation showing this rotation, carefully aligning each frame on the comet's nucleus so it stayed centered while everything else moved around it. The result was mesmerizing. You could see the jets sweeping around like spotlights. You could see the background stars trailing past in smooth arcs as the Earth rotated beneath the fixed stars. You could see the comet as a dynamic, evolving object rather than a static point of light. This kind of time-lapse visualization reveals aspects of comet behavior that single images simply cannot convey. It shows you that comets are active places where things are constantly happening. Material is erupting, the nucleus is spinning, the coma is expanding and being swept back by solar wind. Everything is in motion, everything is changing, even though the timescales are often too slow to perceive with human eyes watching in real time. But speed up time through the magic of time-lapse photography and suddenly that motion becomes obvious. Suddenly you can see the dance of dust and gas around the nucleus. Suddenly the comet becomes less like a fuzzy star and more like the complex object it really is, a mountain-sized chunk of ancient ice and rock that's vigorously sublimating as the sun's heat penetrates its surface. I found myself watching this animation over and over, captivated by the rotation of those jets. Each time through, I noticed new details. A subtle brightening in one region, a slight change in the angle of a jet, the way the anti-tail remained fixed in position relative to the stars while the jets rotated around it. All of these details told parts of the story of what was happening with Comet 3I Atlas. And this brings me back to one of the most intriguing observations from last night. Those jets were definitely shorter than they had been in my earlier observations of this comet. I went back through my archive of images from previous weeks, pulling up the best examples of jet activity I had captured when Comet 3I Atlas was closer to Earth and closer to the Sun. In those earlier images, the jets extended much farther from the nucleus. They were longer, more dramatic, easier to see without having to zoom in quite so much. The change was undeniable. Something had shifted in the comet's activity level, or in how we were viewing that activity, and I spent considerable time trying to understand what might explain this change. One possibility is simply distance. Comet 3I Atlas is getting farther from the Sun with each passing day as it continues outbound on its trajectory toward Jupiter. The Sun's heating decreases with the square of the distance, meaning that as the comet moves away, it receives progressively less solar energy to drive the sublimation of its icy materials. Less solar heating means less vigorous outgassing. Less vigorous outgassing means shorter jets that don't extend as far from the nucleus before the material disperses into the surrounding coma. This would be the straightforward explanation, and it's probably at least part of what's happening. Comets typically become less active as they move away from the Sun, which is why they're brightest and most spectacular when they're near perihelion, their closest approach to the Sun. Comet 3I Atlas passed its perihelion some time ago and is now in the outbound phase of its journey, so decreasing activity would be expected. But there might be more to it than just distance from the Sun. Comet nuclei are not uniform objects. They have different regions with different compositions. Some areas might be richer in volatile materials like water ice or carbon dioxide ice. Other areas might have more refractory materials like rocky dust and organic compounds. As the outer layers of a comet's nucleus erode away through sublimation, new layers with potentially different compositions get exposed to sunlight. It's possible that Comet 3I Atlas has eroded through a particularly volatile rich layer and is now exposing material that's less prone to vigorous outgassing. This could result in shorter jets even if the comet was still receiving the same amount of solar heating. The composition of the surface materials would be limiting the activity rather than the available energy to drive that activity. There's also the question of viewing geometry. The jets we see from Earth are the ones oriented more or less in our direction, or at angles where the ejected material catches sunlight in a way that makes it visible to us. As the relative positions of Earth and the comet change, jets that were previously well positioned for observation might rotate out of view, while other jets that were hidden might become visible. The apparent length of a jet also depends on the angle at which we're viewing it. A jet pointed directly at us or directly away from us will appear shorter than a jet oriented perpendicular to our line of sight, even if they're actually the same physical length. So the shorter jets I was seeing might not mean the jets were actually shorter. They might just be oriented differently relative to Earth than they were during my earlier observations. To really know what was happening, I would need to combine my observations with data from other observers viewing the comet from different locations and angles. Only by compiling multiple perspectives could we build a three-dimensional understanding of the comet's actual jet structure versus how those jets appeared from any single vantage point. This is one of the reasons I'm so committed to sharing my observations publicly and contributing to the collective dataset on Comet 3I Atlas. My images from last night will be combined with images from observers in Europe, Asia, Australia, South America, all around the world. Together, those observations will paint a more complete picture than any one of us could achieve alone. As I wrapped up my processing work and prepared to share the images, I thought about the viewers who would see them. Some would be experienced amateur astronomers who would immediately recognize the significance of features like the prominent anti-tail and the rotating jets. They would understand the technical challenges involved in capturing these images and the care required in processing them to reveal subtle details without introducing artifacts. But others would be newcomers to astronomy, people who had never looked at a comet before, people for whom this might be their first exposure to the idea that you could actually see jets of material erupting from a comet's nucleus. For those viewers, I wanted to provide context and explanation. I wanted to help them understand not just what they were seeing, but why it mattered, and what it told us about these fascinating objects. This is part of why I maintain my channel and why I put so much effort into documenting my observations of objects like Comet 3I Atlas. Yes, the images themselves have scientific value. Yes, they contribute data to researchers studying comet behavior. But they also serve an educational and inspirational purpose. They show people what's possible. They demonstrate that you don't need a professional observatory to contribute to astronomical science or to capture images of remarkable beauty and scientific interest. Anyone with dedication, with willingness to learn, with persistence in developing their skills can do this. Anyone can point a telescope at the sky and capture photons that have travelled across millions of miles of space. Anyone can process those photons into images that reveal the hidden structures of distant objects. Anyone can be part of the great human endeavour to understand our cosmic environment. And right now, with Comet 3I Atlas providing this spectacular show, and with the rare January 22nd alignment approaching, there's no better time to be involved in amateur astronomy. This is the kind of event that people will remember and talk about for years to come. This is the kind of opportunity that defines an observing season and creates memories that last a lifetime. I uploaded my processed images and prepared to share them with the community. Along with the images, I included detailed notes about the observing conditions, the equipment I used, the processing techniques I applied, and my observations about the changing appearance of the jets. This metadata is almost as important as the images themselves because it allows others to properly interpret the data and compare it with their own observations. Citizen science only works when we're transparent about our methods and honest about our limitations. I always try to be clear about what I actually observed versus what might be artifacts of my equipment or processing. I try to distinguish between confident identifications of real features and tentative detections that need confirmation. I try to present my data in a way that's useful to others, rather than just showcasing pretty pictures. Because ultimately that's what this is about. It's about building knowledge collectively. It's about each of us contributing our small piece to the larger puzzle. It's about working together across borders and time zones and language barriers to understand something that no one person could fully comprehend alone. Comet 3I Atlas belongs to all of us. It's not my discovery or any individual observer's private project. It's a shared phenomenon that we're all experiencing together. And the more we pool our observations and insights, the better we'll understand this remarkable visitor and what it can teach us about the nature of comets in general. As the day progressed, and I caught up on some much-needed sleep after my late-night observing session, I kept thinking about the evening to come. The forecast showed clear skies again, which meant another opportunity to observe Comet 3I Atlas. Another chance to document its appearance as we drew closer to that January 22nd alignment. Another night of data collection to add to the growing archive. I started planning the observing session mentally. I would use the same basic equipment setup that had worked well the previous night, but I would make a few small adjustments based on what I had learned. I would start earlier if possible to maximize the amount of time before the wind picked up. I would perhaps try slightly longer exposure times to gather more light and potentially reveal fainter details in the jet structures. I would make sure to capture enough frames for a good time-lapse sequence showing the rotation of the nucleus, and I would pay close attention to that anti-tail, watching to see if it continued to become more prominent as our viewing geometry evolved. If the trend continued, if the anti-tail kept getting brighter and more clearly defined with each passing night, that would be strong evidence that we were indeed approaching an optimal viewing angle of the comet's dust disk. And that would bode well for what we might see on the 22nd when everything aligned perfectly. But I also had to manage my expectations. Astronomy is full of disappointments. Weather doesn't cooperate. Equipment fails at crucial moments. Comets don't always behave as predicted. Brightness estimates can be wrong. Anticipated spectacles sometimes fizzle out into barely visible smudges. I've been doing this long enough to know that nothing is guaranteed until you actually capture the image and see the data with your own eyes. So while I was excited about the upcoming alignment and optimistic about what it might reveal, I was also preparing myself mentally for the possibility that it might not live up to the hype. Maybe the opposition surge effect wouldn't be as dramatic as predicted. Maybe clouds would roll in on the 22nd and block the view entirely. Maybe some unexpected change in the comet's activity would dim it more rapidly than anticipated. Any of these things could happen, and I had to be ready to roll with whatever actually occurred. This mindset of hopeful realism is essential for amateur astronomers. You have to maintain enthusiasm and dedication to keep going night after night, but you also have to accept that nature doesn't always perform on command. The universe doesn't care about our schedules or our expectations. Celestial events happen when they happen, and we either capture them or we don't. All we can do is prepare as best we can and then adapt to whatever actually transpires. As evening approached and I started preparing my equipment for another night of imaging, I felt that familiar mixture of anticipation and nervousness that comes before any observing session. Will the seeing be good? Will the tracking be accurate? Will I be able to focus precisely enough to capture sharp stars? Will the wind stay calm? Will unexpected clouds appear? All of these uncertainties swirl through your mind as you go through the setup routine. But there's also confidence that comes from experience. I've done this hundreds of times. I know my equipment intimately. I know how to troubleshoot common problems. I know what good data looks like as it's being captured. I know when to push through minor difficulties and when to pack it in because conditions have deteriorated too far. This accumulated knowledge and skill doesn't eliminate the uncertainties, but it gives you the ability to work through them and maximize your chances of success. I carried the equipment outside as dusk settled over the landscape. The sky was clear, just as the forecast had predicted. Early stars were becoming visible in the deepening blue of twilight. The air was calm, conditions looked promising. I felt a surge of optimism as I began setting up the telescope mount and attaching the optical tube assembly. Tonight would be another opportunity to observe Comet 3I Atlas, another chance to capture its jets and tail and coma in exquisite detail. Another night of contributing to the collective documentation of this remarkable object during this historic period of rare alignment. And as I worked through the familiar setup routine, adjusting and aligning and testing each component of the system, I thought about all the other observers around the world who were probably doing exactly the same thing at this very moment. In Europe, observers were already deep into their nighttime imaging sessions, capturing Comet 3I Atlas from their longitude as it tracked across their sky. In Asia and Australia, some were finishing up their observations as dawn approached, while others were just beginning. And here in my location, I was joining this global network of dedicated amateur astronomers, all of us pointing our telescopes at the same target, all of us working to document the same phenomenon from our different perspectives. This is the true power of modern amateur astronomy. We're not isolated hobbyists working in solitude anymore. We're part of a worldwide community, connected by the internet and united by our shared passion for observing the cosmos. We share our images in real time. We compare notes about what we're seeing. We help each other troubleshoot problems and improve our techniques. We celebrate each other's successes and commiserate over weather-related disappointments. And when something truly special happens, like this upcoming January 22nd, alignment of Comet 3I Atlas, we're all in it together. We're all working toward the same goal of capturing and documenting this rare event. The images that will be created on that night won't belong to any single observer. They'll belong to the entire community, to everyone who contributed their time and effort and skill to making them happen. As I finished the equipment setup and began the alignment process, I watched Comet 3I Atlas appear in my finder scope. There it was, that familiar fuzzy patch of light, right where the ephemeris data said it should be. I centered it carefully and then switched to the main imaging camera to get a better view. And yes, even in the unprocessed preview images on my laptop screen I could see it clearly. The bright inner coma, the hint of that anti-tail extending in one direction. The overall glow that marked this visitor from the outer solar system. I adjusted focus carefully, using the sharpness of background stars as my guide. Getting precise focus is absolutely critical for astrophotography. Even a small focus error will soften your images and reduce the fine detail you can capture. I zoomed in on a bright star near the comet, adjusted the focuser in tiny increments, watched as the star image tightened to a small sharp point, then locked the focuser in place to prevent any inadvertent shifting during the imaging session. Tracking alignment came next. I needed to ensure the telescope mount would follow the comet accurately as it moved across the sky, keeping it centered in the camera's field of view throughout the night. This involved taking test exposures, measuring how much the comet drifted between frames, and making small adjustments to the tracking rates until the drift was minimized to acceptable levels. It's a tedious process, but essential for good results. Finally, With everything aligned and focused and tracking properly, I started the actual imaging sequence. The camera began capturing frame after frame, each one a long exposure-gathering light from Comet 3i Atlas. And with each new image that appeared on my screen, I could see we were getting good data. The stars were sharp points. The comet was properly exposed, showing detail in both the bright nuclear region and the fainter outer areas. The anti-tail was clearly visible. Everything looked promising. I settled into the rhythm of the observing session. Monitor the incoming images to ensure quality remained high. Check the tracking periodically to verify the comet stayed centered. Watch the sky for any signs of clouds moving in. Listen to the sounds of the telescope and mount to detect any unusual vibrations or mechanical issues. Stay warm and alert despite the late hour and the cold night air. This is the reality of astrophotography that people don't often think about when they see beautiful images posted online. Behind every stunning photograph are hours of work like this: preparation and setup, monitoring and adjustment, patience and persistence. Fighting cold and fatigue and equipment gremlins, it's not glamorous, but it's necessary. And for those of us who love this hobby, it's also deeply satisfying. Because when you capture that perfect frame, when everything comes together and you see detail in your image that you've never seen before, when you realize you've documented something significant or beautiful or scientifically interesting, all of those hours of work feel completely worthwhile. The cold doesn't matter. The fatigue doesn't matter. The frustrations and failures along the way don't matter. What matters is that image on your screen showing you something remarkable. And tonight was delivering those moments. Frame after frame showed Comet 3i Atlas in beautiful detail. I could see the jets even in the unprocessed preview images, which told me they would be spectacular once I applied proper processing techniques. The anti-tail was even more prominent than it had been the night before, confirming my suspicion that it was continuing to strengthen as our viewing geometry improved. The overall brightness of the comet seemed slightly diminished compared to previous nights, consistent with its increasing distance, but it was still plenty bright enough for excellent imaging. As the hours passed and my collection of frames grew, I started thinking ahead to the processing work that would come later. I was accumulating a rich dataset tonight, possibly even better than the previous night's session. The seeing conditions were excellent, which meant the atmospheric turbulence was minimal and the stars were remaining sharp pinpoints rather than bloating into fuzzy blobs. The tracking was spot on, with the comet staying perfectly centered frame after frame, and the wind remained calm, eliminating the vibration issues that had forced me to end early the previous night. Everything was coming together for what would likely be my best imaging session yet of Comet 3i Atlas, and we were still days away from the January 22nd alignment. If tonight's conditions were this good, I could hardly imagine what might be possible on the 22nd itself if we got similar or better weather and seeing. I found myself making detailed mental notes about everything I was observing as the imaging session continued. The way the jets appeared to be positioned tonight compared to the previous night, the brightness distribution within the coma, the length and sharpness of that anti-tail. All of these observations would be valuable when I sat down to process the images and compare them with previous night's data. Pattern recognition is crucial in astronomy. You need to notice when things change, when features appear or disappear, when brightness levels shift. These changes tell you about the physical processes happening with the object you're observing. With Comet 3i Atlas, I was building up a mental model of how it was evolving over time. The jets were definitely shorter now than they had been weeks ago. The anti-tail was becoming more prominent with each passing night. The overall brightness was slowly declining as the comet moved farther from Earth. These were the broad trends I could identify with confidence based on multiple nights of observation. But there were also subtler changes that I was still trying to understand. Variations in the brightness of individual jets from night to night, slight shifts in the position angle of certain features, possible hints of new activity starting in regions that had been quiescent before. These subtler changes required careful analysis and comparison of many images to confirm. You couldn't just glance at a couple of pictures and declare that something had changed. You needed systematic measurements, controlled processing techniques, statistical analysis of brightness levels. This is where amateur astronomy starts to blend into genuine scientific research. When you move beyond just taking pretty pictures and start actually measuring and quantifying what you're seeing, you're doing real science that can contribute meaningful data to professional researchers. I was determined to approach my observations of Comet 3I Atlas with that level of rigour. Yes, I wanted beautiful images to share with the community, but I also wanted quantitative data that could be used for actual scientific analysis. That meant careful calibration of my equipment, consistent processing techniques that didn't introduce artificial changes, detailed record keeping of observing conditions and camera settings, all the unglamorous background work that turns hobby observations into scientifically useful measurements. As midnight approached and then passed, I continued capturing frames. The comet was now high in the sky, at an optimal altitude where atmospheric extinction was minimal. This is the best time to observe any celestial object, when it's as high above the horizon as it's going to get during the night. Lower atmospheric path length means less atmospheric turbulence and less absorption of light. Every photon that reaches your telescope is precious when you're imaging faint deep sky objects, so you want to minimize any losses between the object and your detector. I checked my watch and calculated how much longer I could continue imaging before the comet would start dropping too low in the west. I had maybe 3 or 4 more hours of good observing time before the combination of decreasing altitude and approaching dawn would force me to stop. That would give me somewhere between 50 and 100 total frames if I maintained the current cadence of exposures. More than enough for excellent stacking and processing work. But even as I made these calculations, I was already thinking beyond tonight, beyond even the upcoming January 22nd alignment. I was thinking about the long-term arc of this observation campaign, how I would continue imaging Comet 3I Atlas as it faded and shrank over the following weeks, how I would attempt to capture it in the same frame as Jupiter when it finally reached that vicinity, how I would compile all of my observations into a comprehensive record of the comet's appearance during its passage through the inner solar system. This kind of long-term dedication to observing a single object is one of the most rewarding aspects of amateur astronomy. You're not just taking random snapshots of whatever happens to be visible. You're conducting a sustained observation campaign, documenting changes over time, building a narrative arc that tells the story of the object's evolution. It requires planning and commitment, but the results are so much more meaningful than isolated observations. With Comet 3I Atlas, I'd been following this approach from my first observations weeks ago. I had documented its initial appearance, watched it brighten as it approached optimal viewing geometry, tracked the evolution of its jet structures, measured the development of the anti-tail. And I would continue this documentation all the way through until the comet finally became too faint and small for my equipment to capture meaningful detail. The complete dataset would show the entire visible life cycle of this comet's passage, from first detection through peak visibility and eventual fading. That dataset would be valuable not just to me, but to the broader astronomical community. Researchers studying comet behavior could use observations like mine to validate their models and refine their understanding of how comets evolve. Educational institutions could use the images to teach students about comets and orbital mechanics. Future observers of other comets could reference this documentation to better understand what to expect during their own observations. The work I was doing tonight would continue to have value and impact long after Comet 3I Atlas had faded from view. These thoughts kept me motivated as the night grew colder and my fatigue deepened. When you're standing outside for hours in the darkness, when your fingers are getting numb despite gloves, when your back aches from hunching over equipment, when all you want is to be inside in the warmth, you need a reason to keep going. And for me, that reason was the knowledge that this work mattered, that these observations were contributing to something larger than just my personal enjoyment. Around 2 a.m, I noticed the first hints of a problem. The guide star I was using for tracking calibration started showing some elongation, stretching slightly instead of remaining a perfect point. This could indicate that the atmospheric seeing was starting to deteriorate, or it could mean that wind was beginning to shake the telescope setup. I checked the anemometer reading on my weather station and saw that wind speeds were indeed starting to increase. Not dramatically yet, but the trend was clear. I had a decision to make. Should I push through and try to capture more frames despite the degrading conditions, or should I stop now while the data quality was still excellent? My experience told me that it's almost always better to stop early with good data than to push too far and end up with unusable images. Once seeing deteriorates past a certain point or wind vibration becomes too severe, you're just wasting time and filling up hard drive space with bad frames. but I was also acutely aware that every clear night was precious, especially with the January 22nd alignment approaching. What if this turned out to be the last clear night before the 22nd? What if clouds moved in and stayed for days? I would regret not capturing every possible frame while I had the chance. This internal debate is familiar to every astrophotographer. The balance between quality and quantity, the tension between stopping too early and pushing too late, the uncertainty about future opportunities. There's no perfect answer. You have to make your best judgment based on current conditions and your assessment of the trade-offs. I decided to continue for another hour, monitoring conditions carefully. If the seeing degradation continued or the wind picked up further, I would stop. But if conditions stabilized at their current level, I could gather significantly more data without sacrificing too much quality. It was a calculated risk, but one I felt was justified given the importance of documenting Comet 3I Atlas during this critical period. The next hour brought mixed results. Some frames were excellent, capturing the comet in sharp detail with minimal atmospheric distortion. Others showed clear signs of seeing effects, with bloated star images and reduced sharpness in the comet's structures. I would be able to use the good frames and discard the poor ones during processing, so the effort wasn't wasted. But the inconsistency told me that conditions were indeed deteriorating, and I would need to end the session soon. At 3 a.m, I made the call to stop. The wind was now strong enough that I could see the telescope tube swaying slightly even when there weren't any gusts. The guide star elongation had worsened, and frankly, I was exhausted. Nearly 6 hours of continuous observing had taken its toll, and I needed to preserve enough energy to safely pack up the equipment and get the data processing started. I initiated the shutdown sequence, carefully powering down components in the correct order to avoid any potential damage. As the equipment went dark and silent, I took a moment to just look up at the sky with my unaided eyes. Somewhere up there, invisible without optical aid but definitely present, was Comet 3I Atlas, racing through space at tens of thousands of miles per hour relative to the Sun, shedding material continuously as solar heating vaporized its icy nucleus, creating those jets and tails and the beautiful structures I'd been photographing all night. It's easy to get so focused on the technical aspects of astrophotography that you forget to simply appreciate the objects you're imaging. The equipment and software and processing techniques are just tools. They're means to an end. The end is connecting with these cosmic phenomena, understanding them better, sharing their beauty and significance with others. Sometimes you need to step back from the viewfinder and the computer screen and just look up with your eyes and remember why you started doing this in the first place. I carried the equipment back inside, moving carefully in the darkness. Everything needed to be properly stored and protected. Lens caps replaced, cables coiled neatly, the telescope covered to keep dust off the optics, the camera batteries put on chargers for the next session, all the mundane housekeeping tasks that are part of being an amateur astronomer. Then, finally, I could turn to the data. I transferred all of the night's frames from the camera to my computer, a process that took several minutes given the large file sizes of modern astronomical cameras. While the transfer ran, I made coffee and tried to shake off some of the fatigue. Processing would take hours, and I wanted to at least make a start on it tonight while the observations were still fresh in my mind. The raw frames started appearing in my processing software. I did a quick scan through them, evaluating quality and identifying any obvious problems. As expected, the early frames from the beginning of the session were excellent. Sharp stars, good signal-to-noise ratio, clean captures of the comet's structures. The middle period of the session had produced consistently good data as well. And then the final hour showed the mixed results I had observed in real time, with quality varying noticeably from frame to frame. I started the calibration process, applying dark frames and flat fields to correct for various camera artifacts and optical effects. This is essential pre-processing that improves the quality of the final stacked image. Dark frames correct for thermal noise and hot pixels in the camera sensor. Flat fields correct for vignetting and dust shadows in the optical path. These calibrations turn raw camera data into properly corrected scientific images ready for further processing. Next came registration and stacking. I needed to align all of the frames on the comet's nucleus and then combine them together to improve the signal-to-noise ratio. This is where the magic really starts to happen. Individual frames might show only hints of faint structures, but when you properly stack dozens or even hundreds of frames together, those faint signals add up while the random noise averages out. Suddenly, features that were barely visible in single frames become clear and obvious in the stacked image. I ran 2 different stacking procedures, one aligned on the stars, which would show the comet trailing across the frame as it moved relative to the background stars, the other aligned on the comet itself, which would keep the comet stationary while the stars trailed. Both approaches have value. Star-aligned stacks are good for showing the comet's motion through space. Comet-aligned stacks are better for revealing fine detail in the comet's structures because they eliminate any smearing caused by the comet's movement during the exposure sequence. As the software churned through the calculations, I watched the stacked images gradually emerging, and they were spectacular, even better than I had hoped. The antitail stood out prominently, a narrow spike of light extending from the nucleus. The jets were clearly visible in the nuclear region, multiple distinct features that I would be able to analyze in detail. The overall structure of the coma showed beautiful subtle gradations in brightness, revealing how dust density varied with distance from the nucleus. This was going to be my best dataset yet on Comet 3i Atlas. The combination of good seeing conditions for most of the session, accurate tracking throughout, and a large number of frames to stack had produced results that exceeded my previous night's observations. I felt a surge of satisfaction and excitement as I examined the stacked images. This was exactly what I had been working toward. This level of detail and clarity would allow me to make meaningful scientific measurements and produce images that would genuinely advance our collective understanding of this comet. I began the contrast enhancement and detail extraction phases of processing. This is where you bring out the faint structures without overprocessing the bright regions. It requires a delicate touch and a good understanding of how different processing algorithms affect astronomical images. Push too hard, and you create artifacts that look like real features but are actually just noise or processing glitches. Don't push hard enough, and you leave real features hidden in the data. I used a combination of techniques, layering different processing approaches to optimize different aspects of the image. Convolution to sharpen details blurred by atmospheric seeing and optical effects. Wavelet processing to enhance structures at different spatial scales. Careful stretching of the brightness levels to bring out faint details while preserving information in the bright nuclear region. Each adjustment was applied incrementally, checking the results carefully before proceeding. As the fully processed images took shape, I started to see details that hadn't been visible in any of my previous observations. The jets were not just simple straight lines extending from the nucleus. They had structure. They showed variations in brightness along their length. Some appeared to have slight curves or bends, suggesting that the ejected material was being affected by the comet's rotation, or by interactions with the solar wind. These were subtle effects, requiring high-quality data and careful processing to reveal, but they were definitely there. The antitail also showed more structure than I had realized. It wasn't perfectly uniform in brightness along its length. There were slightly brighter and fainter regions, probably corresponding to denser and less dense concentrations of dust particles. Near the nucleus, the antitail appeared broader, then it tapered to a narrower spike as it extended away. This shape told me something about how the dust was distributed in the comet's orbital plane, with higher concentrations closer to the current position of the nucleus and sparser distributions farther along the orbit. I spent hours working through the processing, creating multiple versions of each image optimized to show different features. Wide-field views showing the full extent of the tail structures, zoomed-in views of the nuclear region showing the jets in detail, enhanced versions bringing out the faintest outer reaches of the coma, color composites constructed from images taken through different filters, revealing the distribution of dust versus gas in different parts of the comet. By the time I finished the initial processing work, dawn was breaking outside my window. I had been up all night, first observing and then processing. My eyes were tired from staring at computer screens. My mind was fuzzy from lack of sleep. But I had a collection of images that I was genuinely proud of. Images that showed Comet 3i Atlas in unprecedented detail from my equipment. Images that documented the comet's appearance just days before the historic January 22nd alignment. I created the time-lapse animation I'd planned, showing the rotation of the jets as the nucleus spun. The effect was even more dramatic than I had anticipated. You could clearly see the jets sweeping around, changing position from frame to frame as the active regions rotated. The background stars trailed smoothly past in graceful arcs, and through it all, the anti-tail remained fixed in position, a reminder that this feature was related to the comet's orbital geometry rather than its rotation. I prepared to share these images with the astronomy community. Along with the images themselves, I wrote detailed notes explaining what I had observed, the processing techniques I had used, and my interpretations of the various features visible in the data. I wanted to provide context and insight, not just post pictures without explanation. As I uploaded everything and began writing the accompanying text, I thought about how to communicate the significance of what I had captured, how to convey to viewers who might not have deep astronomical knowledge why these images mattered, why the jets were important, why the anti-tail was significant, why this whole observation campaign leading up to January 22nd represented something special. I decided to focus on the story, the narrative of this comet's journey through our solar system, the rare alignment that was approaching, the limited window we had to observe this object before it faded from view, the collaborative nature of amateur astronomical observation, with observers around the world all contributing pieces to the larger puzzle. People respond to stories more readily than they respond to raw technical data. If I could frame these observations as chapters in an ongoing story, I could engage viewers more effectively and help them understand why this mattered. The images from last night would be one of the later chapters in that story. We were approaching the climax, the moment of perfect alignment on January 22nd, when the Sun, Earth, and Comet 3I Atlas would be positioned optimally for maximum brightness and visibility. The images I was sharing now showed us getting close to that perfect configuration. The strengthening anti-tail, the still vigorous jet activity despite increasing distance, the overall brightness that remained impressive even as the comet slowly dimmed. All of these features pointed toward the spectacular show we might witness in just a few days. But I also needed to manage expectations and maintain scientific honesty. There were no guarantees about what would actually happen on the 22nd. Weather could interfere, the comet might not brighten as much as predicted, equipment could fail at the crucial moment, any number of factors could prevent us from capturing the definitive images we hoped for. I needed to communicate the excitement and anticipation, while also acknowledging the uncertainties. This balance between enthusiasm and realism is important in science communication. You want to inspire people and get them excited about what's possible, but you also need to be truthful about limitations and unknowns. Overpromising and under-delivering destroys credibility and disappoints audiences. It's better to be cautiously optimistic and then exceed expectations if things go well than to hype something beyond what can realistically be achieved. As I finalized the text to accompany my images, I tried to strike that balance. I explained the significance of the January 22nd alignment based on the scientific literature and Avi Loeb's analysis. I showed how my recent observations were consistent with us approaching that optimal viewing geometry. I expressed my excitement about the potential for spectacular images, but I also acknowledged the uncertainties and variables that could affect the outcome, and I invited viewers to join me on this journey, to follow along as we counted down the days to the alignment, to share in the anticipation and the eventual results, whatever those might be, to be part of this moment in astronomical observation when amateur astronomers around the world would be pointing their telescopes at the same target, all of us working together to document a rare and beautiful phenomenon. The response to my previous posts about Comet 3I Atlas had been encouraging. People were clearly interested in following this story. They were asking questions, sharing their own observations if they had equipment to observe with, expressing excitement about the upcoming alignment. This engagement was gratifying and motivating. It reminded me that astronomical observation isn't just a solitary pursuit, it's a communal activity that becomes richer when shared with others. I hit publish on the new post, sharing the processed images and the accompanying narrative. Almost immediately comments started appearing, other observers sharing their own recent images of the comet, people asking technical questions about equipment and processing techniques, messages of encouragement and anticipation for January the 22nd. The global community of comet watchers was active and engaged, and we were all building toward that pivotal date together. I finally allowed myself to get some sleep, though my mind was still racing with thoughts about the comet and the upcoming observations. In just a few days, we would know whether the January 22nd alignment lived up to its promise, whether the opposition surge effect would dramatically brighten Comet 3I Atlas as predicted, whether the viewing geometry would reveal details and structures that had been hidden before, whether this would indeed be a once-in-a-lifetime observational opportunity, or whether it would turn out to be more modest than anticipated. But regardless of what actually happened on that date, I knew that the journey leading up to it had already been worthwhile. The nights spent observing, the hours invested in processing and analysis, the connections made with other observers around the world, the growing understanding of comet behavior and dynamics, the simple joy of pointing a telescope at a distant object and capturing its light. All of this had value independent of any single observation or image. Astronomy teaches patience and humility. It reminds you that you're part of something much larger than yourself. It connects you to cosmic processes that have been unfolding for billions of years and will continue long after you're gone. It shows you beauty and complexity that most people never take the time to notice, and it rewards dedication and skill with occasional moments of transcendent wonder when everything comes together and you capture something truly special. Comet 3I Atlas was providing all of that and more, and with the January 22nd alignment approaching, the best might still be yet to come. I drifted off to sleep with images of jets and tails and glowing Comet floating through my mind, already dreaming about the observation still ahead. When I woke later that day, I immediately checked the weather forecast for the coming nights. The pattern showed continued variability, with clear periods interspersed with cloudy ones. The forecast for January 22nd itself was still uncertain, showing a mix of clouds and clear skies, depending on which weather model you consulted. This is typical for medium-range forecasts. The atmosphere is a chaotic system, and predicting conditions more than a day or two in advance involves significant uncertainty. All I could do was prepare as best I could, and then adapt to whatever conditions actually materialized. I would have my equipment ready, I would have my observing plan prepared, I would monitor the weather constantly as the date approached, ready to take advantage of any clear periods, and I would hope that luck would be on our side and the skies would cooperate for this important observation. In the meantime, there were still several nights between now and the 22nd. Each one represented an opportunity to gather more data, to continue documenting the comet's evolution, to refine my techniques and equipment setup. I wasn't going to waste these nights waiting for the 22nd. I would observe every time conditions permitted, building up a comprehensive dataset that would show the entire approach to the alignment. I spent the afternoon reviewing the images from the previous night in more detail, making measurements and quantitative assessments that went beyond the initial qualitative evaluation. I measured the brightness of different regions of the coma to create radial brightness profiles, showing how dust density decreased with distance from the nucleus. I attempted to measure the rotation period of the nucleus by tracking the position of specific jets across the time sequence. I compared the length and brightness of the anti-tail with my measurements from previous nights to quantify its increasing prominence. These measurements would form the basis for a more detailed analysis I was planning to write up after the observation campaign concluded. I wanted to create a comprehensive report documenting everything I had observed about Comet 3I Atlas, including not just pretty pictures, but actual scientific measurements and analysis. This report could potentially be submitted to amateur astronomy journals or shared with professional researchers who were studying the comet. At minimum, it would be a valuable record for my own future reference and for other amateur astronomers interested in comet observation techniques. As evening approached, I checked the current weather conditions and the short-term forecast. Clear skies were predicted for tonight, though the seeing was expected to be only mediocre rather than excellent. Still, mediocre seeing was perfectly adequate for comet observation. Unlike planetary imaging, where you need the very best seeing to capture fine details on small disks, comets are large enough and diffuse enough that you can get good results even when atmospheric turbulence is moderate. I decided to observe again tonight, continuing the systematic documentation leading up to January 22nd. Even if tonight's images didn't quite match the quality of the previous night's data, they would still be valuable for tracking changes and building the time series showing how the comet evolved. The setup process went smoothly, benefiting from the experience of previous nights. I knew exactly how to position everything, how to achieve focus efficiently, how to calibrate the tracking. Within an hour of starting, I was capturing science frames with the comet properly centered and tracked. The seeing was indeed mediocre as predicted, with stars showing some bloating and twinkling, but the comet still presented a beautiful sight through the telescope. As I watched the images accumulating, I noticed something interesting. The anti-tail did appear even more prominent tonight than it had been the previous night. This continuing trend strongly suggested that our viewing geometry was indeed improving night by night as we approached the optimal alignment. By January 22nd, if this trend continued, the anti-tail might be spectacularly prominent, possibly the most striking feature of the entire comet appearance. I also noticed that the overall brightness of the comet seemed to be holding up better than I had expected. Yes, it was dimmer than it had been at peak, but the decline was gradual rather than precipitous. This was good news for the January 22nd observations. If the comet maintained reasonable brightness leading up to that date, the opposition surge effect would have something to work with. A comet that was already fading rapidly might not show much brightening even under optimal illumination geometry. The night progressed smoothly, and I was able to capture another substantial data set before clouds began moving in around midnight. Not a full night's worth of data this time, but still enough frames for good stacking and analysis. I packed up the equipment as the first wisps of cloud began obscuring stars, satisfied that I had made productive use of another observing opportunity. The processing of tonight's data revealed exactly what I had suspected during the observing session. The anti-tail was indeed continuing to strengthen and become more prominent with each passing night. When I overlaid tonight's processed image with the previous night's image, carefully aligned to account for the comet's changing position, the difference was subtle but unmistakable. The anti-tail was brighter, sharper, more clearly defined against the background sky. This progression was exactly what you would expect as Earth moved closer to the plane of the comet's orbit, giving us an increasingly edge-on view of the dust disk. I created a comparison animation, fading back and forth between images from different nights over the past week. The evolution was clear when presented this way. Early images showed the anti-tail as a faint feature, barely distinguishable from the general glow of the coma. More recent images showed it becoming progressively more prominent, developing into a distinct spike of light extending from the nucleus. And if this trend continued for a few more days, by January 22nd we should see the anti-tail at its maximum visibility from our perspective. This kind of systematic comparison across multiple nights is essential for identifying real changes versus artifacts of processing or observing conditions. Any single night's observation can be affected by numerous variables. Atmospheric conditions, equipment performance, processing techniques, even your own fatigue level can influence how images turn out. But when you see consistent trends across many nights, when multiple independent observations all point in the same direction, you can be confident that you're seeing something real rather than an artifact. The jet structures in tonight's images showed interesting variations compared to previous nights. Some of the jets I had been tracking appeared to be in slightly different positions, which made sense given the rotation of the nucleus. But I also thought I could see hints of possible new jet activity in regions that had appeared relatively quiet in earlier observations. This was harder to confirm with certainty because the jets were subtle features that required careful processing to reveal, and it was always possible that what looked like a new jet was actually just noise or a processing artifact. To investigate this more rigorously, I would need to do careful photometric measurements of the suspect regions across multiple nights. If there was genuine new activity starting up, it should show as a consistent brightening in that area over time. If it was just noise or artifacts, the apparent feature would vary randomly from night to night without any systematic trend. This kind of analysis takes time and care, but it's the only way to distinguish real astronomical phenomena from the various sources of false signals that can appear in processed images. I made notes about the regions I wanted to investigate further, marking them carefully in my reference images so I could find the exact same locations in future observations. Then, I would monitor those specific areas night after night, documenting any changes in brightness or structure. Over the course of several nights, a pattern would emerge that would tell me whether I was seeing real new jet activity, or whether I was fooling myself into seeing features that weren't really there. This kind of systematic investigation is what separates genuine amateur science from casual hobby observation. It's not enough to just take pictures and make subjective assessments about what you think you're seeing. You need to make actual measurements, apply statistical analysis, test hypotheses against multiple nights of data. Only then can you draw conclusions that have real scientific validity, rather than just being impressions or guesses. As I worked through the processing and analysis of tonight's data, I kept thinking about how all of these individual observations were building toward our understanding of Comet 3I Atlas as a complete object. Each night's images were like puzzle pieces. Individually, they showed interesting features and structures, but when assembled together into a comprehensive dataset spanning weeks of observations, they revealed the bigger picture of how this comet was behaving during its passage through the inner solar system. We could see the evolution of its jet activity over time. We could track the development of the anti-tail as viewing geometry changed. We could measure the gradual dimming as distance from Earth increased. We could document the rotation of the nucleus through the changing positions of surface features. All of these individual pieces of information came together to create a portrait of a dynamic, evolving object responding to the changing conditions it experienced during its journey. And this portrait was being created not just by me, but by dozens or perhaps hundreds of observers around the world, all contributing their own pieces to the puzzle. Someone observing from Europe might catch details during a particularly favourable observing window that I missed due to clouds at my location. An observer in the southern hemisphere might have a different viewing angle that revealed structures hidden from northern observers. Professional observatories with large telescopes and specialised instruments might capture data that was completely beyond the capabilities of amateur equipment. When all of these diverse observations were compiled and compared, the complete picture of Comet 3I Atlas would emerge. No single observer could capture that complete picture alone. It required collaboration, data sharing, and the collective effort of the global astronomical community. This is modern astronomy at its best, with amateur and professional observers working together, each contributing according to their capabilities, all united by the common goal of understanding these fascinating cosmic visitors. I finished the processing work for the night and prepared another set of images to share with the community. Along with the images, I included my observations about the strengthening anti-tail and the possible hints of new jet activity I thought I might be seeing. I was careful to present the jet observations as tentative, explaining that I needed more data to confirm whether this was real or artifactual. This kind of honesty and transparency is crucial in citizen science. You can't just claim discoveries based on marginal detections in noisy data. You need to acknowledge uncertainty and subject your observations to rigorous verification before drawing firm conclusions. The response from the community was immediate and helpful. Several other observers reported that they too had noticed the strengthening anti-tail, confirming my observations independently. One observer with particularly good seeing conditions at their location shared images that showed the jet structures in remarkable detail. And yes, there did appear to be activity in some of the regions I had flagged as possibly showing new jets. This independent confirmation was valuable. It increased my confidence that I was seeing real features rather than artifacts. But other observers cautioned about overinterpreting subtle features in the noisy outer regions of the coma. They shared examples of processing artifacts they had encountered that looked superficially like jets but turned out to be spurious. They recommended specific techniques for distinguishing real features from artifacts, including checking for consistency across multiple frames and comparing different processing approaches to see if suspected features persisted, regardless of how the data was processed. This kind of constructive feedback and knowledge sharing is invaluable. No single observer knows everything, and we all benefit from learning from each other's experiences and expertise. The community serves as a quality control mechanism, helping individual observers avoid mistakes and improve their techniques. It also provides motivation and encouragement, celebrating successes and offering support during inevitable frustrations and setbacks. As I read through the comments and discussions, I felt a renewed sense of excitement about the upcoming January 22nd observations. The community was clearly energized and ready for this event. Observers were checking their equipment, planning their observing strategies, coordinating to ensure maximum coverage across different time zones and locations. Whatever happened on that date, we would have extensive documentation from multiple independent sources. If the opposition surge effect produced dramatic brightening, we would capture it. If the comet's appearance changed in unexpected ways, we would document it. If clouds or other problems prevented some observers from getting data, others would fill the gaps. This distributed approach to observation is one of the great strengths of amateur astronomy. Professional observatories are limited resources with competitive scheduling processes. They can't dedicate night after night to monitoring a single object just in case something interesting happens. But amateur observers can and do exactly that. We have the flexibility to observe whenever we want, for as long as we want, following objects of personal interest without needing to justify our choices to time allocation committees. And when many amateur observers all focus on the same object during an interesting period, the resulting dataset can rival or even exceed what professional facilities can provide. We might not have the largest telescopes or the most sophisticated instruments, but we have numbers, dedication, and the ability to sustain long-term monitoring campaigns. These advantages can more than compensate for our equipment limitations in many situations. I went to bed that night feeling confident that January 22nd would be well documented regardless of what actually happened. The community was prepared. Equipment was ready. Enthusiasm was high. All we needed now was cooperative weather and for the comet to perform as predicted. The weather was beyond our control, but the comet seemed to be behaving according to expectations so far. The anti-tail was strengthening on schedule. The overall brightness was declining gradually but not catastrophically. The jet activity continued even as the comet moved farther from the Sun. Everything pointed toward a successful observation campaign on the 22nd, assuming the weather cooperated. And even if clouds interfered at my location, I knew that observers somewhere would capture the event. The global nature of the amateur astronomy community meant that complete failure was unlikely. Someone, somewhere, would have clear skies and working equipment. The event would be documented even if I personally missed it, though of course I desperately hoped I wouldn't miss it. After all the preparation and anticipation, after all the nights spent observing and documenting the approach to this alignment, I wanted to be there to capture the culmination. I wanted my own images showing Comet 3i Atlas at maximum brightness, under optimal illumination. I wanted to contribute my piece to the historical record of this rare astronomical event. The next few days passed in a blur of continued observations whenever conditions permitted, ongoing processing and analysis of accumulated data, and constant monitoring of weather forecasts for the 22nd. Some nights were clear and productive. Others were cloudy or had such poor seeing that imaging was pointless. I took what I could get, accumulating frames during every viable observing opportunity. Each night's observations continued to show the strengthening anti-tail, confirming the trend I had identified earlier. By now, it was one of the most prominent features of the comet's appearance, rivaling even the brightness of the forward tail being pushed back by solar wind and radiation pressure. The juxtaposition of these two tail structures, one pointing generally away from the Sun and one pointing generally toward it, created a visually striking appearance that made Comet 3i Atlas instantly recognizable in images. The jets continued their subtle evolution as well. I was now fairly confident that there had been some real changes in activity levels in certain regions of the nucleus. Careful comparison of many nights' worth of data showed consistent patterns rather than random variations. Some jets that had been prominent in early observations had faded or disappeared. Others had appeared or strengthened in regions that were previously less active, and the overall length of the jets continued to decrease, though the rate of shortening seemed to be slowing. Perhaps we were approaching some equilibrium, where the decreased solar heating at greater distances was being balanced by exposure of fresher, more volatile rich materials as the outer layers of the nucleus eroded away. These were the kinds of questions that long-term observation campaigns could help answer. By documenting changes over time, we could infer things about the internal structure and composition of the nucleus that weren't directly observable. If activity increased when we expected it to decrease based on distance alone, that suggested compositional variations. If jets turned on and off in particular regions, that told us about the distribution of volatile materials beneath the surface. Every observation added information that constrained our models of comet behavior. As January 22nd drew closer, I finalized my observing plan for that crucial night. I would start observations as soon as the comet was high enough above the horizon for good seeing conditions. I would use slightly shorter exposure times than usual to account for the predicted brightening from the opposition surge effect. I would capture images continuously throughout the night, only stopping if weather intervened or equipment problems occurred. and I would do multiple series with different processing optimizations, some for the faint outer regions and others for the bright nuclear area, ensuring I captured the full range of structures and brightness levels. I also coordinated with several other observers to ensure we would have good temporal coverage. With observers spread across different longitudes, we could create a near-continuous observation sequence spanning many hours, as the Earth rotated and different observers had the comet visible from their locations. This would allow us to track any short-term variations in brightness or structure that might occur on timescales of hours rather than days. The weather forecast for January 22nd updated frequently as the date approached, with different models showing varying predictions. Some showed clear skies for my location. Others showed partial clouds, a few showed complete overcast. The uncertainty was frustrating but not surprising. Medium-range weather forecasting is inherently probabilistic, and you can't know with certainty what conditions will be until you're actually experiencing them. I prepared contingency plans. If clouds were present but broken rather than solid overcast, I would attempt imaging during clear periods between cloud passages. If seeing was poor but transparency was good, I would focus on wide-field imaging showing the overall structure rather than trying to capture fine detail. If conditions were completely unusable at my location, I would still participate by helping coordinate the global observation network and compiling data from other observers. The evening of January 21st arrived, the night before the alignment. I went out to observe as planned, wanting to capture the before state for direct comparison with whatever tomorrow night would bring. Conditions were decent, not spectacular, but adequate for good imaging. I captured another solid dataset showing Comet 3I Atlas, with its now very prominent antitail and its shortened but still clearly visible jets. As I processed these images in the early hours of January 22nd, I realized that this might be my best comparison baseline for evaluating any changes the opposition surge effect might produce. These images were taken just hours before the optimal alignment. Any differences I saw in tonight's images versus tomorrow's would be directly attributable to the changing illumination geometry rather than to longer-term evolution of the comet itself. I stayed up far too late processing the data, driven by anticipation for what was coming. The images were excellent, showing every feature I had been tracking in beautiful detail. The antitail was spectacular, a narrow spike extending impressively far from the nucleus. The jets, though shorter than weeks ago, were still clearly visible, and showed the familiar rotation pattern as the nucleus spun. The overall brightness had stabilized somewhat, declining more slowly than it had been earlier. Everything looked perfect for what we hoped would be a spectacular show in just a few more hours. Finally, I forced myself to get some sleep. Tomorrow would be a long night, and I needed to be alert and functioning well to make the most of the opportunity. I set multiple alarms to ensure I would wake up in plenty of time to check weather conditions and prepare equipment. Then I tried to quiet my racing mind enough to actually fall asleep, despite the excitement and anticipation churning inside me. I woke to my first alarm and immediately grabbed my phone to check the weather. The current conditions showed clear skies. The short-term forecast showed clear skies continuing through the evening and overnight. The seeing predictions indicated good but not exceptional atmospheric stability. All in all, it looked like we were going to get the weather we needed. I felt a wave of relief mixed with excitement. This was actually going to happen. I spent the day in a state of barely contained anticipation, checking weather updates compulsively, going over my equipment checklist multiple times, confirming coordination plans with other observers. The global astronomy community was buzzing with activity as everyone prepared for the night ahead. Social media was full of posts from observers around the world getting ready, sharing their excitement, posting their own equipment setups and observing plans. The sense of collective participation in a significant event was palpable. This wasn't just me and a few other dedicated observers paying attention. This had captured the imagination of the broader amateur astronomy community worldwide. Hundreds or perhaps thousands of people would be watching Comet 3I Atlas tonight, either through their own telescopes or through the images that would be shared in real time as they were captured. As afternoon transitioned to evening, I began my equipment setup earlier than usual. I wanted everything ready and tested well before the optimal observing time. No last-minute rushing or troubleshooting, no discovering problems after darkness had fallen. Everything needed to be prepared and verified in advance so I could focus entirely on the observations once night arrived. The setup went smoothly, almost suspiciously so. Usually there's at least some small issue that needs attention, some adjustment or recalibration required. But today everything worked perfectly on the first try. The mount aligned precisely. The tracking was immediately accurate, focus was crisp and stable. The camera and computer communicated flawlessly. It was as if the equipment knew this was an important night and decided to cooperate fully. As twilight deepened and the first stars appeared, I did final checks of all systems. Everything remained nominal. Weather conditions were holding clear as predicted. Seeing appeared to be quite good based on the sharpness of early test images. All the factors were aligning just as perfectly as the geometric alignment we were here to observe. Comet 3I Atlas appeared in my finder scope right on schedule, exactly where the ephemeris predicted it would be. I centered it carefully and switched to the main camera, and there it was, already showing clearly in the unprocessed preview images. The anti-tail was immediately obvious, that characteristic spike pointing back toward the sun. The overall brightness seemed good, maybe even a touch brighter than last night, though it was too early to be certain. I started the imaging sequence, capturing frame after frame as the sky darkened toward full night. Each new image showed the comet in beautiful detail, and as I watched them accumulate, as I did quick assessments of brightness levels and structure visibility, I began to suspect that something special was indeed happening. The comet looked brighter than it had the previous night, not dramatically, not spectacularly, but noticeably. A subtle but definite increase in luminosity that showed up both in the overall glow and in the visibility of faint outer structures. This could be the opposition surge effect beginning to manifest. As we approached the exact moment of optimal alignment, as the Sun, Earth, and Comet 3I Atlas moved into their perfect geometric configuration, the elimination of shadow effects was causing the comet to brighten just as theory predicted. It was actually working. The rare alignment that Avi Loeb had written about, that had only been documented one other time with a comet, was producing observable effects right before my eyes. I felt a thrill of excitement mixed with scientific satisfaction. This was why we do this. This was why we spend nights in the cold darkness monitoring these objects. Because occasionally, just occasionally, you get to witness something truly special. Something rare and beautiful and scientifically significant. Something that validates all the effort and dedication and persistence that amateur astronomy requires. I continued imaging with renewed intensity, making sure to capture as many frames as possible while conditions remained excellent. Other observers were reporting similar findings in the real-time coordination channels. Multiple independent observers at different locations were all seeing the same brightening effect. This wasn't a fluke or an artifact. This was a real astronomical phenomenon happening right now, being documented by amateur astronomers around the world. The hours passed in a state of focused concentration. Monitor the incoming images, check tracking and focus periodically, watch the sky for any signs of changing conditions, capture frame after frame after frame, building up the dataset that would allow detailed analysis later. This was observational astronomy at its purest, gathering photons from a distant object, accumulating data that would reveal the comet's properties and behavior. Around midnight, I noticed something interesting in the preview images. The jets seemed more prominent than they had been recently. Not longer, but brighter, more clearly defined against the coma. This made sense in the context of the opposition surge effect. If the elimination of shadows was brightening the overall comet, it would particularly affect features like jets where dust particles were ejected from the nucleus. Those particles would reflect more light when viewed in opposition, making the jets more visible even if their physical size and structure hadn't changed. I made sure to capture plenty of high magnification images focused on the nuclear region to document these jets in as much detail as possible. This was the kind of data that could provide real scientific insights into the comet's activity mechanisms. By comparing the jet brightness and visibility under different illumination geometries, and we could learn about the size distribution of dust particles in the jets and about how those particles scattered sunlight. The night continued, productive and exciting. The weather held clear. The seeing remained good. The equipment performed flawlessly, and Comet 3I Atlas put on a spectacular show, brightened by the opposition surge effect, displaying its jets and tails and overall structure in beautiful detail. This was exactly what we had hoped for when planning this observation campaign. The rare alignment had delivered on its promise, producing observable and documentable effects that would contribute to our scientific understanding of comet illumination phenomena. As the hours progressed toward dawn, I knew I was accumulating what would likely be my finest dataset on Comet 3I Atlas. The combination of excellent observing conditions, optimal illumination geometry, and a large number of high-quality frames would allow processing and analysis that revealed this comet in unprecedented detail from my equipment. Every minute of observation tonight was adding value, building up the comprehensive record that would document this historic event. Other observers were reporting their own successes in the coordination channels. Images were being shared in real time, showing Comet 3I Atlas from different locations and perspectives around the world. The brightening effect was confirmed by multiple independent observers using different equipment and processing techniques. The strengthened visibility of jets and fine structure was consistently reported. This was solid, reliable data backed by cross-verification from numerous sources. Around 3 a.m, I took a moment to step back from the eyepiece and the computer screen and just look up at the sky with unaided eyes. Somewhere up there, invisible without optical aid but definitely present, Comet 3I Atlas was racing through space in perfect alignment with the Sun and Earth. Solar photons were striking its dusty coma without creating shadows, bouncing back toward us with maximum efficiency. Ancient ice was sublimating under the Sun's heat, creating jets of gas and dust that streamed away from the nucleus. All of this was happening millions of miles away in the cold vacuum of space. And yet here I was, standing in my backyard, able to observe and document it all through the miracle of telescopic observation and modern imaging technology. Able to contribute meaningful scientific data to our collective understanding of these cosmic phenomena. Able to participate in a global collaboration of amateur and professional astronomers, all working toward the same goal of comprehending our solar system and our place within it. This perspective, this sense of connection to the cosmos and to the worldwide community of observers, this is what makes amateur astronomy so profoundly rewarding. Yes, the images are beautiful. Yes, the technical challenges are engaging. Yes, the scientific discoveries are exciting. But underlying all of that is this fundamental sense of participation in something larger than yourself, of contributing to humanity's ongoing effort to understand the universe, of being part of a tradition that stretches back centuries to the first humans who looked up at the night sky and wondered what they were seeing. I returned to the telescope and continued imaging, capturing frame after frame as the night slowly gave way to approaching dawn. I would observe until the brightening sky made it impossible to continue, extracting every possible minute of data from this historic night. And then would come the processing work, the analysis, the comparison with previous night's observations to quantify exactly how much brightening the opposition surge effect had produced. But that could wait for later. Right now, in this moment, I was focused entirely on the observation itself, on guiding photons from Comet 3I Atlas into my camera's sensor, on building up the dataset one frame at a time, on participating in this rare astronomical event alongside observers around the world, on experiencing the profound satisfaction that comes from successful scientific observation of a remarkable cosmic phenomenon. The eastern horizon began to brighten with the first hints of approaching dawn. Stars started disappearing as the sky background luminosity increased. Comet 3I Atlas became progressively harder to see as it competed with the growing twilight glow. Finally, reluctantly, I captured the last usable frame and ended the observing session.